na panoorin ang ating crash course video, okay? You can also refer to other references in reading Thermodynamics 1. Okay? I know guys, medyo nakaka-overwhelm yung mga equations, yung rami ng formulas and concepts, but don't worry. In our PT discussion, I will give you a summary of equations, okay? So please look forward to that on our PT discussion on July 13th. So now, guys, let's proceed to thermodynamics 2. For today, we will discuss first the second law of thermodynamics, second, free energy criteria for spontaneity, C, combining first and second laws, and D, the third law of thermodynamics. Gina ba, guys? Okay, let's see. Ayan. So for today, we have entropy. Diba? Everywhere we go, guys, entropy is there. Diba? Ang mundo ay masyadong magulo. Diba? Yung utak natin masyadong magulo. Diba? So we can say that entropy is everywhere. Okay? So guys, just a recap on the second law of thermodynamics. Okay? Second law of thermodynamics involves the entropy. So entropy, it is the measure of the degree of disorder or randomness. Okay? And it measures the dissipation, okay, or the distribution of energy. Ayan. So here, we see it, guys, in a solid, we have a more ordered arrangement of molecules, right? There is less disorder, therefore there is lower entropy. Now, when we go to our liquid here, yung nasa gitna, yung molecules, mas lalo silang nagmo-move, okay? And they flow easily. And that corresponds to a higher entropy compared to solids. Now, when we look at our gas here, or for example, water vapor, okay, they are farther apart from each other, okay? And they are freely moving away from the beaker, okay? And this corresponds to more disorder. Kita nyo guys, mas magulo yung ating mga water molecules dyan. And this corresponds to a higher entropy, okay? So, sinasabi lang guys ng ating second law of thermodynamics, okay, when heat is being absorbed into a system, the change in entropy or the delta S becomes positive for a reversible process occurring at a fixed temperature. Okay? Now, bakit guys? Because adding heat gives the particles more energy, right? Pag nag-absorb ng energy ang heat, pag nag-absorb ng energy ang molecules, okay? Di ba yung molecules nag-vibrate? Okay? That's why the molecules will move. Okay? Gets ba guys? And this makes the molecules spread out more freely. Okay. And as a result, the system becomes more disordered and entropy increases. Okay. So a good illustration of this, guys, is the phase transition of ice. Okay. As you can see here. Okay. Meanwhile, guys, for an irreversible process, okay, entropy increases. Okay. It is greater than dq over d. Again, dq represents heat divided by temperature. Okay. So remember these equations, guys. Ayan. So, the entropy of an isolated system increases in the course of spontaneous change. So, yun yung sinasabi ng ating second law of thermodynamics, okay? And in general, guys, the greater the entropy change, then the more likely the process is to occur spontaneously. Again, the greater the delta S, then mas spontaneous ang ating reaction. Okay? So, in general, ito ang mathematical definition ng second law of thermodynamics, which indicates that the total entropy change of the universe, okay? So, yung universe, guys, kinoconsider natin as an isolated system, okay? Sinasabi ng second law that this entropy change increases for spontaneous processes. Okay? And the delta S of a universe consists of the system, the entropy of the system, plus the entropy of the surroundings. Okay? So guys, what is the relevance of the second law of thermodynamics? Bakit nga ba natin siya inaaral? So for example, guys, here we have two systems, A and B. Okay? So they are capable of transferring heat from one another. Okay? So here we have a hot object, letter A, and cold object, letter B. Okay? Now, when they are brought in contact with each other, okay, yung first law of thermodynamics, guys, will just tell us that one system loses the energy. So, for example, napunta yung heat kay cold, okay, the hot would lose energy. Tapos, the cold object would gain the same amount of energy. However, the first law fails to tell us that whether or not the heat will flow from systems A to B or vice versa. Okay? Again, the first law fails to explain to us in which direction will heat flow. Gets ba? So that's where the second law of thermodynamics comes into the picture. Okay. So again, second law of thermodynamics states that heat can flow spontaneously from a hot object to a cold object. So yun yung ine-explain ni second law. Okay. Because the flow of heat from a hot object to a cold object is spontaneous. Guys, heat will not flow spontaneously from a cold object to a hot object. If from cold to hot, ang transfer ng heat, that would be non-spontaneous. Okay? So guys, the second law deals with the conditions of the spontaneous and non-spontaneous direction of heat, or in general, any process. Okay? Ayan. So guys, entropy also is found in reactions, right? So for chemical reactions, the standard entropy change, delta S naught, and standard entropy of formation, delta Fs naught, are determined through the standard entropy values of substances. Di ba guys, meron tayong mga values for delta Fh, di ba? These are our enthalpies of formation. Ganun din guys for entropy, okay? So we have standard entropy values for substances. So how do we determine the standard entropy change or the entropy of a reaction? Okay? So that is delta S naught. So kung may F naught, so guys, tandaan nyo lang to ha. Pag may naught tayo guys, meaning standard. Okay? Meaning this is the entropy change at standard conditions. In standard conditions, which is again 298K and 1 bar. Okay? So delta S naught of a reaction is equal to the summation of the entropy values of the products minus the summation of the entropy values of the reactants. Okay? So for example, for a hypothetical reaction, A plus 2B, which is your reactants, which produces 3C plus 4D, then the entropy change for the reaction is 3 times the entropy value for C. Okay? So 3, guys, because it is the coefficient of the product C, plus 4, which is the coefficient of the product B, times the entropy value, standard entropy value for B. Okay? Minus the standard entropy value for the reactant A. Okay? So ang kanyang coefficient ay 1. That's why it's only S, not A. Minus, oh guys, bakit ako nag-minus? Because we're just distributing the plus sign. So basically, kanina, ganito siya. Okay? Okay? Ganyan. Okay? So, dinistribute ko lang yung minus sign, guys. That's why minus na siya dito. Okay? So, that's minus 2 standard entropy value for B. Okay? I hope that's clear, guys. And with that, let's answer this sample problem. What is the standard entropy of reaction given this reaction where N2 nitrogen plus 3 hydrogen forms ammonia? Okay? So, here we are given the values for the standard entropy values of ammonia, H2 and N2. Okay? Again, guys, ang ating entropy of reaction, standard entropy of reaction is just equal to the summation of the standard entropy values of the products minus the summation of the standard entropy values of the reactants. Solving, we get 2 times 192.5, okay, because your product is ammonia, okay, and it has a coefficient of 2, and its entropy value is 192.5 joules over mole K, minus, okay, so nasa reactant na tayo, 1 times the standard entropy value for nitrogen, which is 191.5 joules over mole K, minus 3, ito, times the standard entropy value of hydrogen, okay, which is equal to 130.6. Getting the standard entropy of reaction, it's equal to negative 198.3 joules over mole K. Okay? So guys, tandaan ha, ang ating SI unit for entropy is J over mole K. Okay? Okay. Diba? Basic pa? Oh, now guys, we have what we call the Boltzmann entropy. So when we say Boltzmann entropy, okay, part ito siya guys ng statistical thermodynamics, okay? Because we are finding entropy through the number of microstates in a system. Diba guys, dati sinabi natin microstates is the number of possible configurations for a system, right? The macrostate is made up of microstates, okay? So, anong nangyayari guys? Ano yung in-explain ng Boltzmann entropy? So, when molecules experience an increase in temperature, diba guys, yung molecules natin nagiging mas distributed over the available energy levels it possesses. And with that, we can obtain the Boltzmann entropy through this equation. Boltzmann entropy S is equal to the Boltzmann constant times Ln omega, okay? Where S is equal to the Boltzmann entropy, Kb is equal to the Boltzmann constant, and omega is equal to your number of microstates. O diba? Very straightforward. Guys, possible na lumabas ito sa board exam. Okay? Now, another way to determine the Boltzmann entropy is through the mole of a material, okay? So that is Boltzmann entropy equal to R, which is just your universal gas constant, times L and W. When we say W, guys, that is the number of orientations. Okay? Guys, I hope that so far, diba? Kayang-kaya naman ang ating Boltzmann entropy. Kayang-kaya ba? Okay, I hope so. So guys, actually, we can obtain the Boltzmann constant through our calculator. Diba guys, ninuruan ko kayo dati how to get the exact value of the mass of protons, mass of neutrons, mass of electrons. So we can also get the exact value for the Boltzmann constant. So the Boltzmann constant is just constant number 25. Okay? So if you have a Canon calculator, just input, shift, convert, or C value, tapos 25, tapos equals, okay? And then you'll get the exact value of the Boltzmann constant, okay? Shift, convert, 25, okay? Equals. I hope that's clear, guys. Now let's proceed to our next sample problem, okay? So let's answer this together. If each carbon monoxide molecule in a carbon monoxide crystal has an equal probability of being situated on a lattice site with one of two orientations, so sabi dito guys, it has two orientations, either CO or OC, then what is the value of the standard entropy at 0 Kelvin? Okay, so how do we solve, guys? This is through the Boltzmann entropy for a mole of material. S is equal to R, L, N, W, okay? Guys, sabi dito, we have two possible orientations. Okay? So yun yung basis natin in determining the entropy. So solving for the Boltzmann entropy, S is equal to 8.314 J over mole K. So that is the units for your universal gas constant times Ln2 orientations. Okay? That is equal to 5.76 times J over mole K. Okay? Take note, guys, the units for entropy can either be J over mole K or J over K. Okay? acceptable both, depending kung ano yung hinihingi sa problem. Okay? Oh, now, let's proceed to our formal discussion of the second law of thermodynamics. Syempre, intro pa lang yung kanina. So, for second law of thermodynamics, we will discuss entropy changes in processes, entropy and phase changes, and the Carnot cycle. So, the Carnot cycle is an application of the second law of thermodynamics. Okay, so Gina, of course, dapat Gina. Okay, so table 13 in your physical chemistry manual summarizes the first and second law, okay, equations. So, this is based on the various processes as shown here. Okay. So guys, when we say isobaric, ito yung mga first law, work, delta U, Q, delta H, and delta S, as well as VTP equations niya. Okay? Ganun din for isochoric, isothermal, and adiabatic. Okay? So guys, kailangan ma-memorize natin to. I know mahirap, pero as long as gets natin yung derivation or yung reason, at the very least, bakit ganito yung mga equations, then guys, kayang-kaya nyo yan. Okay? You have a lot of time to memorize these. So guys, we will just look at here the delta S equations. So for an isobaric process, again, for the PV diagram, we have constant pressure. That's why, as you can see here, constant ang pressure as we go from an initial state to a final state. Okay? And of course, the volume changes. Okay? So for isobaric process, the delta S entropy change is equal to Cp ln T2 over T1 for our reversible process. Tandaan guys, for reversible process, dahan-dahan nating change ang temperature for an isobaric process, okay? Because it is an infinitesimal process. Next for isochoric naman, again, we have a constant volume. See here, guys, from an initial to the final state, same pa rin ang volume, but the pressure changes, okay? So for the delta S, that's equal to Cv ln T2 over T1, okay? Sita nyo, guys, yung differences, Cp, Cv. Again, this is for a reversible process. Next, for an isothermal process, guys, here, okay, the delta S is equal to Nr ln V2 over V1. Okay, guys, so what if meron kayong given number of moles sa isobaric and isochoric? So guys, you can just simply add an N here, okay? So pwede siya maging NCP ln T2 over T1 or NCV ln T2 over T1. So for an isothermal process, again, this equation only applies to reversible processes. And lastly, for adiabatic, okay, the delta S varies, okay? And for a polytropic process, again guys, for polytropic, ang meaning natin dyan ay yung P, yung V, yung T is not constant. Again, for polytropic processes, the P, V, T, they are not constant. Okay? So for polytropic processes, okay, kasi guys, minsan yung mga problems, okay, they would say that the process is adiabatic and polytropic. So in that case, the equation is delta S is equal to Nr ln V2 over V1 plus NCV ln T2 over T1. Then guys, these are the VTP equations relevant for each process, okay? So guys, dapat memorize natin to. Yung mga VTP equations na to are based on the ideal gas laws, okay? Like Charles' law, okay, Boyle's law, etc. So later on, when we get to the gaseous state, we will talk about that more. And of course, na-encounter nyo na to, di ba guys, sa inyong online bridging course. So for an isobaric process, ang relevant equation na pwede natin gamitin ay V1 over T1 is equal to V2 over T2. Meaning lang nito guys, what if may hindi kayo alam na value for the temperature? Hindi nyo alam si T2 or hindi nyo alam si V2. Okay, so you can use this equation only for isobaric processes. Next, for isochoric processes, then you can use this VTP equation, that is P1 over T1 is equal to P2 over T2. Okay, so guys, for example, given kayo ng pressures, okay, pero hinahanap nyo yung final temperature for an isochoric process, then you use this equation. P1 over T1 is equal to P2 over T2. And then for isothermal process, we use the Boyle's law. So P1 V1 is equal to P2 P2. Notice guys, here in the isothermal process, okay, yung variables natin ay si P and V because constant si T, okay? Meanwhile, sa isochoric, ginamit natin si P and T as the variables. Yun yung mga hahanapin na values, okay? Because V is constant. And ganun din for isobaric, V and T ang hinahanap natin because pressure is constant. Then lastly guys, if we have an adiabatic process, important to ha, the VTP equation is P1V1 gamma, o tandaan guys, gamma is equal to Cp over Cv, right? Is equal to P2V2 gamma. Again, Cp over Cv. And this is applicable to reversible process. Okay? I know guys, di ba? Ang napakaraming kailangang i-memorize. Okay? But of course, kayang-kaya niya. Basta alam niyo yung mga definitions ng mga various processes natin. Okay? So let's proceed. Ma'am, how did you get the equations for the change in entropy? So these are the equations, guys. This is how we derive the entropy changes, okay? So first, for an isothermal process, okay? Guys, alam natin that for an ideal gas at constant temperature, isothermal, okay, the reversible heat, okay, dq or delta Q, is just equal to negative delta W, right? And we know that work is equal to PdV. Work is equal to negative PdV, therefore, negative delta work is equal to PdV. Now, guys, we can just change P in terms of nRT over V based on our ideal gas law. Again, PdV is equal to nRT over VdV because P is equal to nRT over V. Next, we know, guys, that the reversible entropy equation is delta S is equal to dq rev over T. Pero guys, kita nyo dito sa ating equation 1, we got as alternative equation for dq rev, and that is dq rev is equal to nRT over V dV. So let's substitute that in equation 2. So delta S is equal to nRT over dV times T, right? Kasi sinubstitute lang natin. And getting the integral of that from V1 to V2, diba? Because here, we have two possible volumes, okay? And ang dV natin, diba? So this is for volume, meaning we are getting the integral from V1 to V2, okay? When we solve that, guys, we get NR, ln V2 over V1. Okay? So, ginawa ko, guys, kinancel ko si T, tapos nilabas ko si NR. Now, we have to get the integral of 1 over V dV. O ano, guys, ang integral ni 1 over V dV, that is ln V, right? And then we get ln V2 over V1 since the integration is from V1 to V2. Okay? Gets ba, guys? So, delta S is equal to NR ln V2 over V1. O, next, for isochoric process naman, so we know again, this is the reversible entropy equation. Okay? Dapat memorize na to, guys, because ito yung standard equation for delta S. Then we know that at constant volume, isochoric, the heat is equal to NCV dt, right? NCV T2 minus T1. Let's just substitute equation 2 to equation 1. So, we get delta S is equal to NCV dt over T. Tapos, i-integrate natin from T1 to T2. Okay? Because we have dt here. Getting the integral, we get NCV. So, yun yung nilabas natin. ln T2 over T1. Because the integral of 1 over T dt is ln T. Okay? Since this is a definite integral, guys, ang ating integral for this is ln T2 over T1. Therefore, this is the equation of delta S for an isochoric process. Next naman, we have, ayan. So, for an isobaric process, okay, again, this is the equation for the reversible entropy. Okay, important yan. At constant pressure, guys, we know that dq rev is equal to NCP dt, right? Based on our thermo 1. So, let's just simply substitute equation 2 ito to equation 1. We get delta S is equal to NCP dt over T. And then we'll get the integral, okay, from T1 to T2 ulit, okay, because we have dt here. So, answering, we get CP or NCP, okay, dapat may N yan, ln T2 over T1. Because again, the integral of 1 over T is ln T. And then lastly, for a polytropic or general process, and then guys, when I say a polytropic, P, V, T is not constant, okay? How do we derive the equation for delta S? So first, we determine the reversible entropy equation. Again, ito yarn. And then for a general ideal gas process, guys, okay, the dq rev is equal to NCV dt plus P dV, right? Diba? Tandaan ang ating previous lesson on this. And then using the ideal gas law, guys, we can just relate PdV, which is equal to nRT over VdV. Okay? And simply just substitute equations 2 and 3 to 1. Ma'am, paano yan? Okay? So again, guys, dq rev is equal to NCV dt. Okay? So this is your delta U. And this is your work. Okay? Kaya, dq rev is equal to delta U plus W. Okay? So substituting, we get delta S is equal to NCV dt plus PdV over T. Okay? Tapos, itong PdV, guys, syempre, kailangan nyo dito i-substitute. So, gagawin nyo siyang, okay, I'll erase first. nRT over V dV. Okay? Tapos, guys, kukunin nyo yung integral nito. Okay? So, how do we do that? Okay, tingnan nyo dito, guys, at fourth row. Delta S is equal to the integral of NCV dt over T from T1 to T2. Notice, guys, sineparate ko si NCV dt and nRT over V dV. Okay? Because these are different variables. Okay? Plus the integral of nRdV over V, right? nRV over dV. Sorry, nR over V times dV, okay? And the integral is from V1 to V2. Getting the integral, guys, we get NCV na nilabas ko, ln T2 over T1 because the integral of 1 over T dt is T2 over T, is T, okay? And then plus NR na nilabas lang natin ulit, ln V2 over V1, okay? I hope that's clear, guys. Okay, I hope it's clear. Paano natin ginawa yung mga integrations? Okay, we have to go back to Math Bridging Part 2 in order to further understand how the integration occurred. Okay, I hope that's clear, guys. So guys, syempre, hindi naman required sa atin na memorize natin yung derivations. Okay, again, hindi required sa atin na memorize ang derivations. Ang important is gets natin paano nangyari, how we arrived in these equations. Okay, so let's have a sample problem. Okay, and this time, lahat na ng variables ang isa-solve natin. A monatomic gas is compressed isothermally at 30 degrees Celsius and reversibly to 3/4 of its original volume. Calculate delta U, delta H, Q, W, and delta S of the system. So here, guys, first, let's determine delta U. Our process is isothermal compression. Okay, so reversible isothermal compression. So we have constant temperature process. So we know that for an isothermal process, delta U is equals to 0. And delta H is also equal to 0, right? So now let's solve for work. So our equation for work for an isothermal process is equal to negative nRT ln V2 over V1. Solving, we get negative 1 mole times 8.314. So ma'am, bakit 1 mole? Because we have a monoatomic gas, okay? And guys, in the first place, okay, so again, Ulit guys, yung 1 mole guys, assumption lang yun. Okay? Because hindi naman siya binigay sa problem. Okay? Again, assumption lang yun. So negative 1 mole times 8.314 J over mole K, so that's R, times 303K. So 303K is just 273 plus 30 degrees Celsius to get the Kelvin temperature. Okay? And that is equal to 303K times ln 3/4. Okay? So guys, sabi dito, nag-reduce to 3/4 of its original volume. Anong meaning nun guys? Yung original volume mo, V1, nag-reduce daw to 3/4. Okay? So V2 is just 3/4 of the original volume. Okay? So if we get that, 3/4 V1 divided by V1, then we can simply just cancel V1, right? Gets ba guys? Paano nangyari yon? Di ba lagi natin ito ginagamit sa ating half-life problems? Okay? So parang lang rin siyang in-apply sa ating thermodynamic problems. Okay? So ln 3/4, that's equal to 724.7 joules. Okay? Next, let's solve for Q. Okay? So we know that delta U is equal to Q plus W. Okay? So Q is equal to delta U minus W, and we know that delta U is equal to 0. So 0 minus 724.7 joules. So Q is equal to negative 724.7 joules. Okay? Now, ano lang kulang natin guys? Syempre, ang ating delta S entropy change. And our equation for an isothermal process of delta S is equal to NR ln V2 over V1. Solving, we get 1, again, assumption lang yung 1 mole, times 8.314 J over mole K, times ln 3/4 pa rin. Okay? And that is equal to negative 2.39 joules per Kelvin. Okay? So again, guys, this is a standard unit for entropy. Okay? So when you cancel this, okay, and wala namang units to, ang matitira na lang ay si J over K. Okay? Okay. Ayan, another sample problem. So guys, please solve first. Okay? Pause nyo muna yung video and try to answer. Okay, let's answer. So the pressure of a mole of oxygen is increased by increasing the temperature from 25 degrees Celsius to 50 degrees Celsius at constant volume. Calculate the delta U, delta H, Q, W, and delta S of the system. Guys, when we say constant volume process, ano yan? We have an isochoric process, okay? So let's solve. Yeah. So first, let's get delta U, okay? So the delta U for an isochoric process is NCV delta T, okay? Solving, we get 1 mole, okay? This is given, times 2.5 R. So guys, kailangan natin mag-refer sa CP and CV tables natin to get the value of CV, okay? So guys, tandaan, oxygen is what type of molecule? It is diatomic, right? That's why its CV is equal to 2.5 R, okay? Times the change in T. So that's T2, the final temperature, that's equal to 50 plus 273 Kelvin, so equal to 323 Kelvin, minus 298 K, so that is the initial temperature, 25 degrees Celsius plus 273. Solving, we get 519.6 joules, okay? Next, we solve for delta H. So for delta H for an isochoric process, that is NCP delta T. Solving, we get 1 mole times 3.5 R. So based on the table, CP value is equal to 3.5 R times 323 minus 298. We get 727.5 joules. Take note guys ha. Okay? When we say R, syempre dapat wag mo kalimutang times 8.314. Okay? Baka makalimutan nyo. Mahirap na. Okay? And the next, work is just equal to 0, right? Because again, for an isochoric process, work is just equal to 0. Now, let's solve for Q. So based on our equations last time, Q for an isochoric process is equal to NCV delta T, which is equal to 1 mole times 2.5 R, yun yung CV nyo, times 323 minus 298 Kelvin. There we get Q is equal to 519.6 joules. And lastly, we can solve for delta S. So delta S is equal to NCV ln T2 over T1. Okay, so this is our equation for an isochoric process, and that is equal to 1 mole times 2.5 R, which is your CV, times ln 323K divided by 298K. Solving, we get delta S is equal to 1.67 joules per K or per Kelvin. Okay? Guys, I hope that's clear. Kailangan ng maraming practice. Okay? Di ba sa InOrg marami tayong practice? Siyempre, mas lalo na sa FEChem, guys. Okay? Practice lang talaga ang katapat niyan. Ayan, guys, let's proceed to Carnot cycle. Again, this is an application of your second law of thermodynamics, okay? So what is the Carnot cycle? Okay, so the Carnot cycle is the most efficient cycle possible for a heat engine, okay? It is very theoretical, and it is made up of 4 reversible steps happening between 2 temperature reservoirs, P1 and T2, okay? So we have here a hot reservoir, P1 or TH, and a cold reservoir, T2 or TC, okay? Okay, makinig. So step 1, here we have isothermal expansion, okay? Here it occurs at T hot. Okay. So here, guys, gas will absorb heat, QH, from the hot reservoir. And then it will expand slowly as it absorbs heat. And in that effect, the gas will do work on the surroundings. Okay. And as it does that, okay, temperature stays constant. Okay. So guys, yung piston na yan, nagmo-move up slowly. Okay. As heat flows in. Next, step 2, we have adiabatic expansion. Okay. So here we have no heat exchange. Here, guys, the gas will continue to expand, right? Okay. Yung piston, gumagalaw pa rin ang gumagalaw. Okay, until it cools down to reach the temperature T cold. Okay, again, it will reach a certain temperature called T cold, TC, okay, or T2. Okay. So guys, again, we have no heat exchange in adiabatic expansion. And then step 3, we have isothermal compression. Okay. So this occurs in a temperature cold or TC. Okay. Here, guys, ang nangyayari, since na-achieve na ang TC, the gas will then be compressed. And as the gas is being compressed, as we push the piston, okay, the gas releases heat to the cold reservoir. Ang nare-release na heat ay si QC. And while it does that, the temperature TC stays constant. Okay? So again, we are pushing the piston down and the gas gives off heat, but it stays at the same cool temperature TC. And then lastly, our last step is the adiabatic compression. Okay? Again, we have here no heat exchange. Okay? So mas lalong nako-compress, mas lalong napupush towards the downward direction ng ating piston. Okay? And dahil dyan, yung heat, okay, babalik siya to T-hot. Okay? So as we do adiabatic compression, guys, the temperature goes back to T-hot or T1. Okay? So basically, we need one last push where the gas will heat up without gaining heat. Okay? So bakit siya nag-gain ng heat, guys? Bakit nag-return tayo sa temperature hot or sa T1? That is because we used work, okay? We used work in order to compress the gas, okay? And that is your Carnot cycle. So guys, I hope that's clear. Okay? So another way to view the Carnot cycle is this. Okay? Here again, step 1 is isothermal expansion. Here, Q is in, so nag-absorb ng heat ang gas. Step 2, adiabatic expansion. Okay? Step 3, isothermal compression. Okay? And as this happens, okay, heat is being released by the gas to the cold reservoir. And lastly, we have adiabatic compression, okay, where the temperature goes from the T cold to T hot. Okay? Okay, guys, let's proceed. So the following parameters are measured for Carnot engines. Okay, so these are the parameters shown in your table 14. First, the compression ratio. So it is the ratio of volumes at the start and end of compression. R is equal to Vmax over Vmin. So guys, sa lahat ng mga volumes na makakalculate natin for a Carnot cycle, okay, we just get the compression ratio through Vmax over Vmin. Next, mean effective pressure is equal to total work produced per volume of the cylinder. So that is equal to PME is equal to the net work, okay, divided by Vmax minus Vmin. Again, this is the total work produced per volume of the cylinder, okay? Because again, guys, the Carnot cycle occurs in a gas in a cylinder, right? Tapos may piston ka sa kanyang taas. Next, we have the efficiency. So we can calculate for efficiency, okay, which is a fraction of heat from the high temperature reservoir, which is yung hot, that is converted into work. So di ba guys, yung initial natin na temperature ay T hot, okay? So this is from the hot reservoir, right? So yung fraction of heat from the hot reservoir, okay, di ba, as we go through the Carnot cycle, nako-convert siya into work. Di ba? Di ba? Okay, so with that, the efficiency is equal to output over input. Okay? Now guys, how do we solve Carnot cycle-related problems? Okay? So guys, meron akong shortcut sa inyo. Guys, diretso na tayo sa shortcut ha. Okay? Minsan lang naman lumalabas sa board exam ang Carnot cycle. So guys, dapat maximize natin yung time natin in answering sa board exam. Therefore, kung lilitaw man ang Carnot cycle sa board exam, let's have the most efficient solution as possible, okay? So this shortcut will definitely be helpful to you. So step 1, number each step from the given problem from 1 to 4, okay? Since we have, right, 4 steps, okay? And then 2, tabulate the given VT values on below table, okay? So guys, dapat uniform sila ng mga units. And then solve for the missing PV and T values from the table using the given VTP equations in table 13. Diba guys? O, given tayo ng mga isothermal and adiabatic processes, paano naman natin makukuha yung P, V, and T? Diba guys, kanina may binigay na VTP equations sa atin. So yun yung gagamitin natin, okay? O guys, take note sa step 2, optional lang ang 4, okay? So guys, usually, dapat hindi na natin to i-solve, okay? We can simply determine the parameters for a Carnot cycle, for example, work, Q, delta H, delta U, delta S, compression ratio, mean effective pressure, and efficiency using just the values from steps 1 to 3. Okay? Again, okay na, from steps 1 to 3 lang ang titignan natin, okay? And then, once you know the PVT values, guys, we calculate for work, Q, delta H, delta U, delta S, compression ratio, mean effective pressure, and efficiency. Okay? Oh, how do we do that? Okay, so of course, we have a sample problem. So guys, sabayan nyo lang ako, okay? Consider a Carnot cycle that is operated using a diatomic gas, initially at 25 degrees Celsius, 100 kilopascal, and 0.01 cubic meters. The system is then compressed isothermally. So isothermal compression, yung first step, yun yung number 1 nyo. Okay? Until the volume is 0.002 cubic meters. It is then compressed again into 0.001 cubic meters. Calculate the maximum pressure and compression ratio of the engine. So, let's solve using the steps provided to us earlier. So guys, ano yung sinabi ko? Yung steps natin, yung 1, 2, 3, and 4, it corresponds on the given problem. Okay? Again, hindi sa fact na dapat Di ba sa Carnot cycle, yung step 1, isothermal expansion. Okay? Step 2, adiabatic expansion. Hindi yun, guys. Okay? Yung 1, 2, 3, 4, okay? It depends on the problem. Okay? So let's analyze. Yung first step natin, guys, so from 1 to 2, that is your isothermal compression. Okay? Di ba? Sabi, guys, yung initial daw is 25 degrees Celsius, 298K. And then we have pressure equal to 100 kilopascals and volume of 0.01 inverse cubic meters. Okay? Tapos guys, nagkaroon ka ng isothermal compression. So, after isothermal compression, given dito guys that the new volume is 0.002 cubic meters. Okay? And here, di ba sabi dito isothermal. So we know that the temperature will stay constant after isothermal compression. Therefore, your temperature after isothermal compression is 298. Okay? Kaya may 2 dito. Okay? Tapos, hindi natin alam si P. Next naman, guys, after daw the isothermal compression, okay, the system is compressed again into 0.001 cubic meters. Guys, hindi sinabi na adiabatic or isothermal, but we know that after isothermal compression, sa Carnot cycle, ang nangyayari ay adiabatic compression. So, from 2 to 3, we have adiabatic compression. So, guys, hindi ko nasa-solve si 4. Okay? Kasi, guys, pwede na natin ito i-solve na problem na hindi kailangan C4. Okay? Pero if we know the Carnot cycle, okay, then we would know that 3 to 4 should be isothermal expansion. Okay? But again, we don't need that. Okay? So, iso-solve lang natin ay yung values ni P, V, and T based on these steps. Okay? So, for after adiabatic compression, ang given lang natin ay C volume, which is equal to 0.001 cubic meters. Ito. Okay? Clear, guys? Ayan. So, now, let's solve for the missing values. So, first missing value is the pressure. Okay? So again, from 1 to 2, we have isothermal reversible compression. Based on our VTP equations, we use this equation, P1V1 is equal to P2V2. Okay? Solving, we get 100 kilopascal times 0.01 cubic meters. So ito yung initial mo. That's equal to the P2, which is yung hinahanap natin, yung unknown, times 0.002 kilopascals, which is the V2. That is the volume after the isothermal compression. Solving, guys, so shift solve lang, get the P2, which is equal to 500 kilopascals. Okay? Next, guys, okay, we get the values for our pressure and temperature after adiabatic and polytropic compression. Okay, so ito yung gagamitin natin equations, guys. Ito yung gagamitin natin VTP equations. P2V2 gamma is equal to P3V3 gamma. Okay, makinig, guys. So, to find P3, okay, ito, this is the equation we will use. So, P2, okay, so we know that it is 500, right? Kasi na-solve na natin kanina, times P2, which is 0.002 cubic meters, to the power of 1.4, okay? Because this corresponds to your gamma, Cp over Cv. So, kailangan nyo kunin ang Cp over Cv for a diatomic gas. Okay, so look at your table, guys. Ano ang value for Cp? Ano ang value for Cp? Okay, diba? It's 7 Cp over Cv, okay, gamma, is equal to 7 over 5 or equal to 1.4 based on your table. Equal to P3, which is your unknown, times 0.001 cubic meters, which is given to the power of 1.4. Solving, we will get P3, which is equal to 1,320 kilopascals. Next, guys, meron akong i-introduce na bagong equation. Please take note of this. T2V2, the power of gamma minus 1 is equal to T3V3, the power of gamma minus 1. So that we can solve for T3. Solving, we get T2 is equal to 298K times 0.002 to the power of 1.4 minus 1. Okay? Kasi yun yung equation natin. That is equal to T3, okay? Yung unknown, times 0.001 to the power of 1.4 minus 1. Solving, we get T3 is equal to 393.2 Kelvin. Okay? So guys, actually, we can just simply derive this equation from this equation. Pero syempre, we will not explain that anymore, okay? Because masyadong mahaba na yarn. So now, these are our PVT values. Complete na ang ating table. Now, with these data, we can finally compute for the maximum pressure and compression ratio. Guys, when we say maximum pressure, yun yung maximum pressure attained by the Carnot cycle. O guys, sino ang pinakamalaking pressure? It is P3. Therefore, our maximum pressure is 1,320 kilopascals. Next, for the compression ratio, this is equation Vmax over Vmin. So the maximum volume for the diatomic gas in a Carnot cycle is 0.01 cubic meters. Ito, siya yung pinakamalaking volume, right? Divided by the minimum volume, yung pinakamaliit na volume na attained, which is 0.002 cubic meters. Solving, we get 0.01 divided by 0.002. That's equal to, ilan guys? 5. Okay? So the compression ratio of the engine is 5. Diba? Very easy. Ayan. So now guys, let's analyze the efficiency of Carnot engines. Okay? So tandaan nyo lang that a heat energy will convert thermal energy, it will convert heat into mechanical work. Pero syempre guys, yung efficiency nito is very limited. Okay? Depending on the temperatures of the hot and cold reservoirs. Okay? Now, this limit is being described by the Carnot efficiency. Okay? And the Carnot efficiency will prove us that there is no such engine na 100% efficient. Okay? Kasi in order to be 100% efficient, the cold reservoir must be at absolute 0 Kelvin. Okay? So guys, with that, let's differentiate a Carnot engine and a Carnot refrigerator. Okay? A Carnot engine, guys, would turn heat into work, while a Carnot refrigerator would use work to move heat. Okay, pansin yun guys, kay Carnot engine, gumamit ka ng heat to convert it into work. Kay Carnot ref, it used work to move heat. Okay, so for example, here in Carnot engine, which acts like a perfect heat engine, di ba, nag-absorb ka ng heat, QH, from a hot reservoir. Okay, for example, ito yun. Okay, and then, ang effect niyan ay, part of that energy, okay, part of that energy will be converted into work. Diba? Palabas siya. Okay? And then heat will also be out. Okay? So, diba, some of the absorbed heat will be converted into work, and then the rest will be converted as heat and rejected to a cold reservoir. Again, some, okay, most of it will be used as work, okay, generated as work, and then the rest of it will be generated as heat, okay, in the cold reservoir. In general, guys, QH, okay, yung inabsorb na heat is just equal to the work generated plus QC, rejected to the cold reservoir. Next, for the Carnot refrigerator, so it acts like a perfect cooling device, okay? This time, guys, okay, nag-remove tayo ng heat, QC, from a cold reservoir dito. Okay? Now, a Carnot ref would need work. You need to input work, kita nyo, papunta siya sa refrigerator, in order to operate. Because of that, meron tayong ma-release na heat, QH. Okay? Ang QH, yung heat ay ma-release into the hot reservoir. What is this? Okay? And same pa rin yung equation, guys. Okay? The heat released to the hot reservoir for a Carnot refrigerator is equal to the work inputted plus the cold heat or the heat from the cold reservoir, okay, na nilagay sa ating Carnot ref. Okay? Guys, I hope that's clear. So this table summarizes the types of Carnot engines. Again, Carnot heat engine converts heat into usable work, generates work with the release of residual heat. So yun yung QC nyo. Okay? In general, yung energy balance IQH is equal to QC plus W, right? Siyempre guys, for a Carnot engine, dapat energy should still be conserved. Okay? Energy is still conserved. Diba? It is transformed into QC and work. Okay? And now the efficiency of the Carnot engine is equal to N is equal to output over input lagi, guys. And we know that our output is work, right? We generated work divided by QH. We inputted heat from the hot reservoir, right? We absorbed heat from the hot reservoir. And this is just equivalent to work is equal to QH minus QC. So this is based on this equation divided by QH. Okay? Pag aayusin natin ang equation na yan, okay, we would simplify it to 1 minus QC over QH, diba? Because QH over QH is just equal to 1. Okay? So 1 minus QC over QH. In relation to that, guys, the efficiency of the Carnot engine is therefore equal to 1 minus TC over TH. Okay? Next, for a Carnot refrigerator, again, it converts work, so may na-input kang work, in order to remove a certain amount of heat. Okay, so the coefficient of performance of the Carnot refrigerator. So guys, when we say coefficient of performance, okay, it is related to efficiency. So parang din siyang efficiency. That is equal to output over input. Again, our output is the QC, right? So basically, guys, naglabas tayo ng heat from the cold reservoir. Again, naglabas tayo ng heat from the cold reservoir. That's why it is the output divided by the work. So yung work, guys, yun yung in-input natin, right? It takes work, okay? So solving, we would get QC over QH minus QC, okay? So this is just based on this equation, okay? So when you transpose or when you isolate W, we would just get QH minus QC, right? And then this equation is just equivalent to TC over TH minus TC, okay? Lastly, for Carnot heat pump, it converts work, okay? So again, may input kang work in order to supply a certain amount of heat. So medyo similar siya to refrigerator, okay? So guys, ang coefficient of performance natin or efficiency of the Carnot heat pump is COP is equal to output. So yung output nyo, guys, is QH. Okay, because we want to supply QH divided by work. Okay, so work is the inputted work, right? And that is equivalent to QH over QH minus QC. Again, because work is equal to QH minus QC based on this equation. And this is equivalent to TH over TH minus TC. Okay, I hope that's clear, guys. Now let's solve the sample problem. A Carnot engine operates between two heat reservoirs. So we have T is equal to 400K for one reservoir and T is equal to 300K for another reservoir. For each cycle, the engine receives 1,200 calories of heat from the reservoir. Determine the work produced and calculate the efficiency. So here, guys, okay, yung TH natin is basically the temperature from the heat reservoir, okay? So we have the higher temperature, K. Higher temperature, 400K. Next, for the temperature from the cold reservoir, that is equal to 300K because it is lower, okay, in temperature. And lastly, QH, okay, is equal to 1,200 calories, okay? So meaning, guys, ayun, ito yung na-receive nyo na amount of heat from the hot reservoir. Ito yung inabsorb na heat from the hot reservoir in order for it to generate work, okay, in order for it to produce work. Here we are to determine the work produced and calculate the efficiency. So how do we do that? It is through this equation, guys. Diba, guys? Again, tandaan, the efficiency, N, is equal to work over QH because this is your output, work, divided by QH, your input, right? Ito yung in-input mo na heat. Then that is equivalent to 1 minus TC over TH. Ma'am, bakit ito ginamit ko? Because ito yung mga given sa atin, okay? Hindi naman tayo given ng QH and QC. So solving, we get work is equal to QH times 1 minus TC over 2 TH is equal to 1,200 calories times 1 minus 300 over 400 Kelvin. And that is equal to 300 cal. Ma'am, bakit ka nag-times ng QH? Because we transpose QH to the right side of the equation. Okay? Gets ba, guys? Again, we transpose QH to the right side of the equation. So this is the work produced for this Carnot engine. And then let's determine the efficiency. Okay? So efficiency, again, is just equal to 1 minus TC over TH. Again, it is given. Okay? So efficiency is equal to 1 minus 300K over 400 Kelvin. And that equal to 0.25 or 25%. Okay? So what can we say, guys, about the efficiency of that Carnot engine? It is very low. Okay? Tama naman, di ba? Next, for the additional second law statements, okay, so we have some statements of the second law because of the engines, because of the Carnot engines, okay? So sabi ni Kelvin and Planck, guys, it is impossible for a system operating cyclically, so in a cycle, such as a Carnot cycle, to convert heat into work without rejecting any heat to a cold reservoir. Sinasabi lang, guys, okay, impossible na wala kang mare-reject na heat, any excess heat to a cold reservoir, okay? Ito ang usually nangyayari, okay? Gets ba, guys? So, bawal, guys, na puro work lang ang napaproduce. Okay? For a Carnot engine, bawal na puro work lang ang mapaproduce. Meron ka talagang excess na mapaproduce as heat in a cold reservoir. Okay? And then, the Clausius statement states that it is impossible for a system to spontaneously transfer heat from a lower temperature to a higher temperature in a cyclic process. Okay? So again, we cannot spontaneously transfer heat from a lower temperature to a higher temperature. Meaning nito, guys, heat naturally flows from a hot object to a cold one. Di ba? Na-introduce na natin pa kanina. Okay? Now, for heat to flow in the opposite direction, that is from lower to higher temperature or from a cold object to a hot object, okay? Then dapat work must be done. Okay? Again, work must be done to transfer heat from a lower temperature to a higher temperature. O, di ba? Applicable to sa ating what type of Carnot machine, guys? It is Carnot refrigerator. Kasi 'di ba, gumamit tayo ng heat from the cold reservoir, okay? And then in order for it to be used, okay, gumamit tayo or nag-input tayo ng work. Okay? Ayan. Now let's proceed, guys, in entropy and phase changes. 'Di ba, guys, nag-calculate tayo ng enthalpies of phase changes. So syempre, maka-calculate din natin yung entropy and phase changes, okay? So tandaan, guys, yung ating heating curve of water, again, hindi basta-basta madedetermine ang final temperature ang final entropy, okay? Because ang ating solid ice ay maraming pinagdadaanan, okay? Here we have, again, latent heat and sensible heat, okay? So if there is a temperature change, delta S is equal to Cp ln T2 over T1, okay? So kailan nga nangyayari, guys, ang temperature change, okay? That is when sensible heat is being produced, right? Sensible heat. Next, kapag phase change naman ang nangyayari, where we produce latent heat, the delta S is just equal to the delta change H. So ito yung constant, guys, the enthalpy of phase change divided by the T change. Okay? So later you will see that. Okay? Again, take note of these equations, guys, ha? Iba to sa ating delta H equations for phase changes and temperature changes. Okay? So this table shows the entropy changes among phase transitions. Okay? So dalawa yan. First is the entropy change of fusion. Okay? Kapag melt ang solid to liquid. Okay? This is the entropy change when 1 mole of substance absorbs delta H, okay, delta H fusion at melting point. Again, our melting point for water is 0 degrees Celsius, okay? So the equation again for the entropy change of fusion is just delta Fs is equal to delta Fh over Tf. Next, entropy change of vaporization, that's delta Vap S, okay? This is the entropy change when 1 mole of liquid will be boiled reversibly, okay? Ang nangyayari dito, guys, may delta Vap S tayo because we absorb delta Vap H at boiling point. Again, boiling point is equal to 100 degrees Celsius. So delta Vap S is equal to delta Vap H divided by the temperature of the boiling, okay? Gets ba, guys? I hope gets yan, okay? Then these are the equations, okay? Oh, so yung delta change, guys, so yung change na yan, can either be the fusion, kunwari may melting ka, or vaporization. Okay? Ayan. So this just shows the constants of water. So guys, magagamit pa rin natin to in calculating the entropy and phase changes. Okay? Ayan, so let's try to solve using the same sample problem as in thermodynamics 1. So calculate the total entropy involved with the conversion of 100 grams water from ice at 250 Kelvin to steam at 450 Kelvin. Okay, again, S means sensible heat, L means latent heat. So delta S, due to the temperature change or due to the production of sensible heat, that is, delta S is equal to Cp ln T2 over T1. Okay, sorry, I mean the absorption of sensible heat. Again, sensible heat is absorbed. Okay. Next, delta S due to the phase change or latent heat. So here, latent heat is absorbed. So the delta S due to the phase change is equal to delta change H divided by T change. Okay? So let's try to solve. So guys, step by step natin to ulit gagawin, okay? Para mas magets natin. So same pa rin guys na dapat meron tayong naka-multiply na mass. So dapat dito guys, okay? Meron tayong mass. Dito rin dapat meron tayong mass. Okay? So let's try to solve. Ma'am, bakit may mass? Again, guys, these values of the enthalpy changes, the phase, and the constants of water, it is in terms of grams, right? That's why we have to cancel grams, okay? So first, step 1, here we have ice at 250 Kelvin. When you increase the temperature, okay, it will become ice with a temperature of 273 Kelvin. This is equal to 0 degrees Celsius, and this constitutes your melting point, okay? So equation for that is, the delta S equation for that is 100 grams times 0.5 cal over G, okay? So this is the constant, okay? For fusion, di ba? Again, tingnan natin, guys. This is the specific heat capacity for ice, right? Okay. Times ln 273 divided by 250K, okay? Because this is your final temperature so far, T2, okay? Based on this equation. Plus, okay, delta S due to phase change or as latent heat is absorbed. So that is based on this equation, right? Delta change H. The delta change H here, guys, is the entropy of fusion, right? Because we have melting. So the value for the enthalpy change for fusion is equal to 80 cal over grams divided by the temperature change. Ano yung temperature change? So, siyempre, yun yung ating melting point, which is 270 Kelvin plus 1. Okay? So, this is your specific heat capacity for liquid water, 1 cal over grams times Kelvin times ln 370. Okay? So, di ba, yung liquid nyo, guys, nag-i-increase na ang kanyang temperature until 370 K or 100 degrees Celsius, which is equivalent to the boiling point, okay, over 270 K. Again, this corresponds to the absorption of sensible heat. And then, add nyo naman, guys, this time, the conversion or the transformation of the liquid to steam, right? So again, guys, this occurs at the boiling point, 100 degrees Celsius or 373 K, and latent heat is absorbed, okay? So here, we have delta change H, so that this time it is your delta VAP H, which is equal to 540 cal over grams divided by the T change. So your T change is the boiling point, which is 373 Kelvin, plus, or last na, di ba nag-increase pa further yung temperature from 373 Kelvin to 450 Kelvin. So we take into account the sensible heat absorbed. So the delta S for that is equal to 0.48 cal over GK. So this is a specific heat capacity for steam, okay, times ln 450 K, which is your final temperature T2 divided by T1, 373 Kelvin. Solving, we get delta S is equal to 219 cal over K. Okay, I hope it's clear. Ayan. So now we are down to our next topic. This is free energy criteria for spontaneity. Here, guys, we will discuss first the spontaneity criteria, second, Helmholtz free energy, and lastly, Gibbs free energy. Okay. So for spontaneity criterion, okay, we have two types. So for spontaneous reaction at constant T and V, okay, the condition is that the Helmholtz free energy change, which is dA TV. So yung sub TV, guys, meaning constant ang temperature and volume, it must be less than 0. Okay, dA must be less than 0 or equal to 0. Okay, and the example of this is the combustion of gasoline. Hindi ko rin alam, guys, kung saan ko na ko yung example na yan. Okay, so this is just an example of the combustion of gasoline. Again, this is a spontaneous reaction at constant temperature and volume. Next, for a spontaneous reaction at constant temperature and pressure, the Gibbs free energy change must be less than or equal to 0. An example of this is the rusting of iron. So this is a spontaneous reaction at constant T and V. Now, guys, let's discuss the two types of free energies, okay? So for a closed system under constant temperature and volume, the Helmholtz free energy predicts the spontaneity of a reaction, okay? Na-apply natin siya in combustion reactions and measurements of surface tension. So that is dA is equal to du minus TdS. Basically, guys, okay, Helmholtz measures the usable energy in a system at constant temperature and volume, okay? Bakit tayo, guys, nagsasubtract ng energy loss to entropy? Okay? Because some of it, guys, in Helmholtz free energy, okay, some energy is lost to entropy. Kaya tayo may minus TdS. Okay? So at constant T and V, we care about how much energy is actually available to do some useful work. Okay? Again, TS is just the part of energy lost to entropy. So this is IUTAS. Ang tawag ko dito ay IUTAS. For a closed system naman, under constant temperature and pressure, the Gibbs free energy predicts the spontaneity of a reaction. Okay? Mas common siya than A, guys, because actual experiments are more conducted in constant pressure than in constant volume conditions. Okay? So the formula is dG is equal to dH minus TdS. So that's agatas. Ang tawag namin dito ay agatas. So other ways to write it is delta A is equal to delta U minus T delta S. Ito naman, delta G is equal to delta H minus T delta S. Agatas, ayutas. Okay? Nasabi lang dito, guys, for a closed system under constant TNT, if dG is more negative, then a reaction spontaneously transforms the reactants into the products. Okay? Ayan. So let's move on to another summary of Helmholtz free energy and Gibbs free energy. Let's compare them, okay? So Helmholtz free energy, we define it as the maximum non-pressure volume work at constant temperature and volume. Gibbs free energy naman, it is the maximum non-pressure volume work at constant temperature and pressure, okay? And it is the Helmholtz free energy, it is the energy required to create a system, again, at constant T and V. Gibbs free naman, energy required to create a system at constant T and P. So again, as I said earlier, Helmholtz, less applied siya because kailangan mong gawing constant ang volume ng system. And this is harder, right? In real life situation, it is hard to keep the volume of the system constant. However, Gibbs free energy, lagi to or mostly to ginagamit sa lab, sa experiments, right? Because it finds more application because it's easy to make a system have a constant pressure, okay? And in general, guys, dapat negative ang sign sila when reactions are spontaneous, okay? So guys, please watch this video to further understand the contribution of delta H and delta S to our Gibbs free energy.
Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 59. It's on using Gibbs free energy, which is essentially energy that's available to do work. So if I were to push this sphere right here, it's going to move down and it's going to move back. Where's the energy coming from? Well, that would be gravitational potential energy being converted to kinetic energy. Eventually, it comes to rest at the bottom. But if we think of this as an analogy, it really explains what's going on in a chemical or physical process. What we have is reactants, and we have products. Those reactants are moving towards products. Spontaneously, some are moving back, and eventually it reaches equilibrium. What's happened to our Gibbs free energy? It's gone to zero. And so we look at Gibbs free energy. It's a really good indicator of if we have a spontaneous reaction or a non-spontaneous reaction. So if Gibbs free energy is ever negative or less than zero, then we know that we have a spontaneous reaction. We have a scenario that looks like that, where we have energy and that energy can be released. If we have a delta G greater than zero, then we have a scenario that looks something like this. We have an uphill reaction. It's not going to occur spontaneously. In other words, we're going to have to put a little bit of energy in for it to work, and then finally we can have equilibrium in the middle. Now in the last video, we learned that the two things that really contribute to Gibbs free energy is enthalpy and entropy. In other words, those two things together can help us determine if it's a spontaneous reaction or a non-spontaneous reaction. But it doesn't answer every question. In this video, I'm going to try to answer every question. What's missing is our temperature. In other words, T is going to be incredibly important. And so if we're trying to figure out if it's a spontaneous process or not, one of the biggest things is enthalpy, or the amount of internal energy. And so if we have a delta H that's negative, that's a good indication that we're going to have a spontaneous reaction. So in a thermite reaction, our reactants have more energy than our products. It's a downhill reaction, and so we'd expect this to occur spontaneously. Likewise, if we were to rust iron, same thing. We're going to have more energy before than we do after. That energy is going to be released. That energy is going to be released into the surroundings. But sometimes you'll have exceptions to that rule. So like a coal pack, if you think about that, it occurs spontaneously, but in fact, it's actually consuming energy. And so we're going to have a delta H that's going to be a positive value. And so we can't just stick with enthalpy by itself. We have to add entropy to that. So if I had these two spheres and I had gas on the left side and I just open it up, we're going to see that gas move from left to the right. So we're going to have this irreversible process. And so what's going on there, we're not changing the energy. What's really going on is entropy. And so these two things together, enthalpy and entropy, are very important in helping us figure out if this is a spontaneous process or not. So we could put it on a grid like this. And so if we ever have a decrease in enthalpy, so that's going to be an exothermic reaction, or one that increases entropy, we know immediately that's going to be a spontaneous reaction. Likewise, if we have the opposite of that, if we have an increase in enthalpy and a decrease in entropy, we know that's going to be non-spontaneous. Now, the nice thing about that is the reverse of that we can automatically figure out is going to be spontaneous. But what's going to be in these other two spots? What's going to happen, for example, when we have an endothermic process, but we're actually increasing entropy, or vice versa? And so a good place to look at that is just the movement of ice to water. So if we're looking at ice and water, if we look at the molecules of ice, there's going to be a huge amount of order there. And a lot of that has to do with these hydrogen bonds. If we look in liquid water, it's going to be moving around. And so if we were to move from ice to water, what's that process? That's simply melting. That's going to be an increase in delta H. What does that mean? That's going to be an endothermic process. It's taking energy from its surroundings. So we're going to have a delta H that's positive. What's happening to our entropy? Our entropy is increasing. In other words, our matter is becoming more dispersed. So where would that be over here? We have an increase in enthalpy, and we have also an increase in entropy. And so let's go in the opposite. Let's say that we're actually freezing that water. What's going on there? We have an exothermic reaction. So we have a decrease in enthalpy, and we also have a decrease in entropy. And so this is going to be this block right here. And so in other words, if we could figure out this one slide, it would help us unlock what's in these other two grids right here. And so what do you know? Well, you know that if we take ice and we have it in an area where our temperature is greater than 0 degrees Celsius, this is going to be a spontaneous reaction. In other words, if you ever take ice and put it in an area where it's warmer than 0 degrees Celsius, we know that ice is spontaneously going to melt. Likewise, if we take that water and put it in an area where it's less than 0 degrees Celsius, then it's going to freeze. And we also know that if it's exactly at 0, we're not going to see any change. It's going to be non-spontaneous in either direction. So we've really answered this question right here. So if we were to look at that melting, if we ever have an increase in enthalpy, so this is a endothermic reaction, and an increase in entropy, that will be spontaneous as long as we have a high enough temperature. Likewise, if we have a decrease in enthalpy, so it's an exothermic reaction, and a decrease in entropy, then that's going to be spontaneous, but only at low temperatures. And so now we can finally come to Gibbs free energy, that equation, and hopefully it makes sense at this point. So if we're to look at Josiah Willard Gibbs' equation, this is going to be delta G on the left side. Remember, if it's ever less than 0, we know this is a spontaneous reaction or process. If it's ever greater than 0, we know that it's non-spontaneous. And so it totally makes sense, this grid right here. If you have a decrease in this number, that's a negative value. And if you have an increase in entropy, so our delta S is going up, since we're subtracting it, that's going to give us a negative value. Likewise, if we go down to this non-spontaneous right here, what do we have? We have a delta H, which is going to be a positive value. That's going to make this value go up. And then our delta S, since it's negative, we're subtracting a negative, so that's going to be a positive. And so hopefully these two make sense. But now this should unlock this grid right up here. So what happens if we increase our enthalpy? Well, if we're increasing our enthalpy, you would start to think, well, this is going to increase our delta G. But if we have a high temperature, that's going to make our entropy more important since we're subtracting that value. And so we can get away with a low enthalpy or a positive enthalpy if we have a really high temperature and an increase in entropy. Likewise, same thing down here. In this case, if we can have a decrease in this enthalpy, but our entropy, even though it is going down, we have a really low temperature, it's not going to swing us as much. Now, this also unlocks that whole idea of a cold pack. What's going on there? Well, we have an endothermic reaction. Again, it's taking energy from its surroundings. Our delta H is a positive value. And so why are we getting a spontaneous reaction? Since we have a delta H, it's going to be a positive value. Well, we're moving from ammonium nitrate into ions of ammonium and ions of nitrate. And since we're doing that, we're increasing our entropy. And so since our delta H value is going to be so big, then we're going to have a spontaneous reaction. We're going to have an overall delta G that's going to be a negative value. And so again, Gibbs free energy and that equation is really powerful because it tells us exactly what's going to happen in that process. If it's less than 0, it's going to be spontaneous. It's greater than 0, it's going to be non-spontaneous. If it's equal to 0, we're at equilibrium, and I hope that was helpful.
Okay, guys. So that sums up the AGA and how delta H and delta S determines the spontaneity of reaction. Okay. So, guys, okay, with that in mind, okay, we can finally generalize what he said earlier based on table 16. Okay. So, guys, when we have a negative delta H, so that occurs for exothermic reactions, and we have a positive entropy, okay, we have a negative delta G. Okay. And tama naman, di ba? Because okay, when you draw the delta G, which is equal to delta H minus T delta S, when this is positive, okay, and this is negative, then we know, guys, that this will be negative. Therefore, it is spontaneous at all temperatures. Next, if the delta H is negative, exothermic, however, the entropy decreases. Okay, ang example nito kanina, guys, diba, is when water freezes into ice, right? Delta G would either be positive or negative. Specifically, it is negative or it is spontaneous at low temperatures. Okay? So, for example, delta G is equal to delta H minus T delta S. So, guys, kung very low ang iyong T, okay, and then you have a very negative delta S, hindi magiging positive to, guys, right? So, this is negative. Therefore, delta G would be more negative, okay? And so on and so forth. So, if you have a positive delta H, so this occurs for endothermic reactions, and you have an increase in entropy, okay? You have either a positive or negative delta G, and it is spontaneous at high temperature. So, example natin, guys, dito is the melting of ice, right? So, in the melting of ice, it is an endothermic reaction because it absorbs heat, okay? And again, liquid water, syempre, it has greater entropy than ice, right? Therefore, we have a positive delta S. So, the only time where the reaction will be spontaneous is at high temperatures, because if this is very high, guys, if this is plus, tapos plus din ito, if this is very positive, okay, we will get a more negative value for delta G. And lastly, guys, if you have an endothermic process, so positive delta H tapos negative ang entropy, matik, guys, positive ang delta G, okay? It is non-spontaneous at all temperatures. So, guys, you don't have to actually memorize it, okay? You can just simply, okay, derive this from this equation, okay? Now, let's proceed to our sample problem. At what temperature will a certain reaction start to be spontaneous? The delta H and the delta S of the reaction are 115 kilojoules and 210 joules per Kelvin, respectively. So, guys, tandaan ang ating equation dito. We have a given delta H and given delta S. We are to determine the temperature at which the reaction will start to be spontaneous. Guys, kailan magsa-start maging spontaneous ang ating reaction? When delta G is what? Syempre, dapat less than 0. Okay, again, delta G is less than 0. Okay? So, at delta G is equal to 0, guys, equilibrium na, di ba? Now, when we get to delta G less than 0, then the reaction will be spontaneous. So, let's solve. Let's assign delta G as equal to 0. Okay? That's equal to 115 times 10 to the power of 3 joules minus T, which is your unknown, times 210 joules over Kelvin. Okay? So, guys, sinasabi lang dito na, sinaset natin to 0 because this reaction is in equilibrium. Okay? And the answer is, when we shift solve, that's equal to T is equal to 548 Kelvin. So, guys, at temperatures, okay, 548 K and above, okay, the reaction will be spontaneous. Okay, second, at what temperature will a certain reaction start to be spontaneous? The delta H and delta S of the reaction are 85 kilojoules and 150 joules over Kelvin respectively. So guys, we also use the Agatas equation. Solving, we get 0 again on delta G is equal to 85 times 10 to the power of 3 joules, which is your delta H, minus T, which is your unknown, times 150 joules per Kelvin. Solving, we get T is equal to 567 Kelvin. So dapat guys, okay, T 567 Kelvin and above, okay, the reaction will be spontaneous. Okay. Ayan. Now, Gibbs free energy is also being calculated in isothermal processes. Okay. So yung mga equations na to guys are derived from the fundamental equation dG is equal to VdP minus SdP. So later I will introduce our fundamental equations. So for delta G, for an isothermal process, that's equal to nRT ln V1 over V2. Or delta G is equal to nRT ln P2 over P1. To derive guys, okay, from the fundamental equation of dG, the partial derivative GBT, meaning GPT, so the change in G with P, with pressure, as the temperature is constant, that is just equal to the volume V. Okay. So getting delta G is equal to the integration of V dP. Okay. Again, it is based on this equation. Okay. Now, so basically guys, nilipat ko lang si dP sa right side. Okay. Again, nilipat ko lang si dP sa right side. So naging dG V dP. Okay. Tapos kinuha ko yung integration. Okay. Getting the integral from P1 to P2 because we have a change in dP here, we get delta G is equal to nRT over P because guys, tandaan, based on our ideal gas law, V is equal to nRT over P, right? And this is equal to nRT. So nilabas na natin si nRT, the constants, times the integral of 1 over P dP. Again, guys, the integral of 1 over P dP is delta G is equal to nRT ln P2 over P1. Because guys, the integral of this is just ln P. Okay? Ayun lang naman. Now let's proceed. Now we can also determine the standard delta G. So the standard Gibbs energy change of a reaction is determined from the standard enthalpies and entropies of the reaction. So ito. Okay? It can also be calculated using the standard Gibbs energy change of formation, delta Fg, of the reactants in product. So same as what we did in the standard entropy change, okay, in standard enthalpy change. Again, delta G naught is equal to the standard enthalpy change minus temperature times the standard entropy change of the reaction, okay? Now again, these are applicable to reactions. Second equation, delta G naught for a reaction, that's equal to the summation of the Gibbs energy change values for the products minus the summation of the Gibbs energy change of a reaction of the reactants, okay? Now here guys, we can calculate delta G in chemical reaction. So very relevant ito sa ating electrochemistry, okay? So the Gibbs free energy spontaneity criteria is useful in determining the equilibrium composition of reaction mixtures, okay? So the two equations we use is